Alright, now notice, we now have added polyatomic. I think we've added this, I think we talked about polyatomic in a different chapter as well. Right? Because we talked about how poly really just means 3 or more. Okay? So yeah, if so 3 or more atoms is what poly means. Poly means 3 or more. Maybe I should remove the atoms. Poly just means 3 or more. But now, does it say anything in this definition that would suggest that it has to be the same element 3 times?
No.
So, Jared wasn't in here, I would say something about that quiz question. Which you all got wrong.
Get out, Derek.
So, I'm not going to do it. But you can probably figure out what my question might be.
Nope, can't figure it out.
I know what it's about.
It's all.
You might be able to answer, you would be able to answer that one problem. Nah, I can't say anymore.
Well, now that he's learning this, he's gonna know.
That's why I never did it.
Eric,
Okay?
get out. Go on, I'm just saying.
So, if you notice, each of these guys have how many atoms? 3.
Right.
Okay? In fact, I guess there is one way where you could do all 3 atoms identical. Now, does this mean that if all 3 atoms are identical, I still can't call it a polyatomic molecule? No, because it says 3 or more atoms. It doesn't say anything about them having to be identical or not having to be identical. So that would encompass whether they're identical or not, both.
So that would just mean it's either a polyatomic molecule or a polyatomic element.
But remember when we talked about how all diatomic elements are diatomic molecules?
Yeah.
Right? By definition. Okay. Polarity. This is where we're going to spend a significant amount of time today. We're going to have to go back and review electronegativity. Electronegativity. Ugh. I shouldn't have had that Cheeto. That made me more hungry.
Well, lunch is
I guess I do have my last. You're not allergic to cashews, are you?
I am.
No, I think so.
My sister is.
So if I like breathe cashew scented breath, it wouldn't make you.
I'm fine with everything with breathing. I just have to eat it and then I blow up.
Oh.
Oh. Have you ever accidentally eaten something that you're
So.
You say yes?
No.
You've never you've had stuff you're allergic to?
Yeah, no.
You said you blew up. You're still here.
Yeah, she didn't specify that it blew up.
But
Like
you
a puffer
said every
fish.
time you have it, you blow up.
No.
What you
Just
said?
for just nuts.
Pardons in your yes.
Have you ever had nuts?
No. Any nuts.
Wait, you're allergic to
Except
all
coconut.
nuts?
What?
You're allergic to all nuts?
All. You can have
Oh,
Walnuts.
Not do.
all nuts.
Oh, walnuts.
No, yeah, I'm allergic to walnuts and all nuts except coconuts.
Why'd you say all nuts instead of coconuts? Why'd you say allergic to walnuts plus all nuts? Doesn't all nuts make it walnut be part of that all
Stevie
nut?
heard all nuts, she heard
Oh, are
walnuts.
you actually?
No, I heard all nuts. People heard walnuts.
And
I heard all nuts.
Okay.
Oh, that's what I heard.
Yeah.
Okay.
Not or
I'm so
peanuts.
confused. Basically, I can have coconuts but nothing else.
Does that mean coconut isn't a nut?
Coconut is not. Technically not, it's fruit.
Peanuts aren't even nuts. They're like beans.
True.
Oh my gosh, what are nuts?
Yeah.
They're
Alright, hey.
They look beautiful.
This actually is a pretty big lesson, so.
Okay.
What's the lunch today?
Spaghetti.
What kind of
They don't do it right. They have like little
Getting an eating sauce?
Yeah. How do you like more than 4 to bring up as
Hey, how about you twirl your pencil and write some words?
What am I twirling around?
Get a little-
Not literal, figuratively here.
Oh, that was a 5. You're doing 5.
My dad told my coach that I was very literal. Yes.
What do you think?
He told my coach that I was very literal. She told me to go get the ball during my game. So I went to the ball, but it was actually, I was supposed to go to the girl that was gonna get the ball. So.
Did not keep the 1.
Oh, yeah, I was thinking of this one. No, Cindy, not that one! No, after they yelled at me to go to get the other girl, I was like, oh, now I feel stupid. And then you know we were doing zone we were on. Oh, yeah. You're like, well, because we started zone this whole time. Yes, we started and she said to do man offense. And then she switched it like in the middle and she didn't know that it was called thunder. Like our zone offense is called thunder. And she yelled thunder, but she didn't know that's what that meant. I never heard thunder. She yelled thunder. Oh, I never even heard that. Because I knew what thunder was.
Good day. Sounds like you're making a lot of mistakes. Alright, we done? Okay. Polarity. Here's how polarity is created. Do you guys remember what electronegativity is?
Yeah.
What is it?
How much?
Strongly they attract.
Like
To other
how the
atoms.
poles are.
How much an atom
One.
pulls on electrons when bonded? Okay? Okay? So when different nonmetals share electrons, so let's say I'm doing this, those are two different nonmetals, correct? They're sharing an electron, that's a covalently bonded Lewis structure. Their electronegativities are going to be different because they're not identical, correct?
Yeah.
What that means is that the electrons that are being shared are not shared what?
Equally.
Okay? Do you remember which of these two guys is more electronegative?
Fluorine.
Fluorine is. The trend is least electronegative, most electronegative. Okay? This is an exception, it's kind of in the middle of the range. Okay? Okay, let's talk more about this. The shared electrons are going to be more likely to be found near the element with the higher electronegativity. Why? So, what does electronegativity mean?
How strongly
How strongly they pull. Right? Or attract, same thing. Right? If you strongly attract something, you have a strong pull for it. Okay, so these two electrons here are being bonded. Okay, this has a stronger pull than this. Does this mean these electrons are going to sit here right in the middle?
No.
No. You ever played tug of war with someone stronger than you?
Yeah.
Kind of like that.
I choose not to keep that.
Okay? So what ends up happening is the more electronegative is going to have a stronger pull, so the electrons are going to spend more of their time closer to the one that has a stronger pull. Okay? That creates polarity, and I'll explain as we progress what that does.
Oh my goodness. What? Yes, Cindy. Yes.
It's a stronger pull, stronger polarity.
Poles and North Pole.
Didn't you guys just beat the North Pole?
No, we didn't.
Oh,
We played
how many-
but we were
How many
asking
puns can we do?
Poland.
Poland really likes polarity.
They all have push doors.
What?
Everybody has push doors?
No, they have pull doors.
In Poland.
Yeah, they have pull doors.
All right, we're wasting time. I'm wasting time. Polarity.
together.
It's a little more complicated than that, but on the right track. Got it? Okay. So this just tells you what the name is called when they do not share equally. It says when electrons are not shared equally, you get a polar covalent bond. We know covalent means shared. Polar just means not shared equally. Okay? And it says one end has a positive charge and the opposite end has a negative charge. Let me show you how this works. Let's assume, let's compare hydrogen with hydrogen versus hydrogen with fluorine. These two guys are the exact same element, so they pull exactly the same, so the electron's going to be perfectly in the middle, creating a nonpolar, is what we would call it. Here we've got fluorine that's more electronegative. It has a stronger pull, so the electrons are no longer in the middle. Now remember, in these two guys, if they're completely shared perfectly equally, I take two neutral atoms, bond them together, and they share their electrons perfectly equally, is there going to be any charge with that particular molecule if the electrons are shared perfectly equally and they were neutral to begin with? No. Okay? But if I start unequally sharing and I take the electron that made this hydrogen neutral and I pull it this direction, it's going to create charge. Okay? Now, the side of the molecule where the electrons get pulled will have a negative charge. Why? This side doesn't have as many electrons?
No.
If I'm taking the shared electrons and I'm pulling pulling it to the right, wouldn't that make this side become a little bit more negative than this side? Because electrons are negative. And I take electrons and I shift them to one side, wouldn't that make that side become negative?
Yeah.
And if I remove electrons or take electrons away from this side, wouldn't that probably make this side positive? If I'm shifting electrons from one side to the other, that's going to make the side that I shifted to them negative, and the side I took them away from positive. So here's what happens. This is exactly how things are held in the solid and liquid state. You have a positive end of one molecule is attracted to the negative end of another molecule, and that's how we get solid and liquid states. This guy, there's no polarity. And what is hydrogen typically at room temperature? What state? Gas. Because they're not attracted to each other. Thought there. We'll talk more about that when we take higher level chemistry. Alright, so here's really what the definition of polarity is. I'll write it. You want to write it. Here's the definition of polarity. So when you deal with guys with different electronegativity values, one pulls more than the other, which creates opposite regions of opposite charge or polarity. I know it's the same word twice, but what do I mean when I say opposite regions? If I say opposite regions, what do I mean? What's the opposite region of where I am right now? Over there. So opposite ends. That makes sense? Is this opposite this region-wise? Yes. And are they opposite in charge? Yes. Make sense? Now, those opposite regions of opposite charge, or the polarity, is created by what? What creates the polarity? Well, not all bonds are polar bonds, though. What creates polarity? Yeah, different electronegativity values. If they were the same electronegativity values, would you have polarity? They're shared completely equally, so it would be a completely neutral guy. You with me, Shane? You look like you're falling off into la la land. Now I'm just going to talk about this a little bit. We hit this a lot more in chemistry as we get more advanced. The first time you've heard it, we're dealing with some pretty difficult vocabulary here when we're talking about electronegativity values and what they mean. You're probably not going to be able to understand polarity if you don't know what electronegativity is. Okay, so it might be a little struggle early on as we try to work through this, but then when you take chemistry, you'll see it again. We'll spend some more time talking about it. You should have a far better grasp at that point. But it says here, depending upon how you arrange your polar bonds, you can actually get an entire molecule that's not polar. And I know that's hard for you to understand, but let's just say I'm doing this guy now. Just going to show you this. Some of you, this might go over your head. I'm not sure. We'll find out. I'm not going to expect you to do this on a test. I'm just going to show you what I mean. Okay, if I'm just talking about this bond, is it a polar bond? Yes, why? Okay. I'm looking for a word, it's really important. They have different electronegativity values. If they're different elements, they have different electronegativity values. I'm just telling you that right now. So that is a polar bond, which means it's not going to be equally shared electrons, correct? Okay? Well, which one is more electronegative based on our trend? Fluorine. So which direction would the electrons shift? Towards the?
Fluorine.
So like this, and like this, and like this, and like this. Correct? Okay? Alright, so if I'm just focusing on this side of the molecule here, and I have electrons pulling in this direction, what would that create? What charge would be here? It would be negative, because that's where the electrons are being shifted, right? How about here? How about here? How about here? Does this have polarity? This molecule have polarity? No. What is the definition of polarity? Opposite regions of opposite charge. Opposite regions? Same charge. So you can have polar bonds, and still have a non-polar molecule. Okay, now that's next level stuff here. Okay, because they're pulling in opposite directions, so they essentially counteract each other. Really, the positive region is right in the middle. Okay, this guy is actually a gas at room temperature. Because if I take another molecule like this and put it close, wouldn't I have two negative sides no matter how I arrange it, I'd have a negative side and try to do a negative side. Does that ever happen? Do negatives attract negatives? No. So do you think it will be solid form if they don't attract each other? Do you think they'll be in a liquid form if they don't attract each other? What form do you think they'll be in? Gas. Yes.
Is that a weird symbol? Apologize or apologize?
This is a Greek symbol. It's what they use to represent the partial charges that's created when you have polarity.
I was just asking.
No, it's a Greek symbol. Yep. Okay?
For it to be a test, you need to limit that consistency.
Yeah, that's true, that's pretty good.
Yeah, okay? So, depending upon whether or not how a molecule is arranged, it could be polar or could not be polar. Okay, and that has a pretty important impact on its shape. So we'll end talking about shape and a few properties. And I'm just gonna introduce this stuff because we just got done in the chemistry chapter doing molecular geometry, where they had to memorize 8 different geometric shapes and how to identify them. Okay, so we're just getting a taste here. Now, I'm not expecting huge understanding at this point, just broad picture, broad understanding. Big picture here. Okay, diatomic. What does it mean?
2 atoms.
2 atoms. Diatomic molecule is 2 atoms. Diatomic element is 2 of the same element. Okay? So, no matter how I write something, if I only have 2 objects, is there any way I could get a nonlinear shape? Like, how do I make 2 objects that are bonded to each other ever be a shape that's not a straight line? Is it possible? You got 2 points and you connect them with a dash. Straight line every single time, no matter what. Does that make sense? No matter how I do it. If I can do it like this with fluorine. That was the most random way to do that. But that's still a straight line, right? This is a vertical straight line, but it's still a straight line. Or maybe like carbon with oxygen, which this is a goofy one you've probably never seen. Okay, that's a more higher level Lewis structure. You're probably wondering, how is that possible? Oxygen actually takes an electron, or carbon actually takes an electron from oxygen. It's higher level, yeah. Higher level. Okay? No matter what, linear. Now, these 2 are diatomic elements, could also be diatomic molecules. This one can only be a diatomic molecule because it's not a diatomic element because it has different elements. Okay. Alright, and then it says some polyatomic molecules are not linear. You can have polyatomic molecules be linear, but there are situations where you can have polyatomic molecules that aren't linear. Here would be an example. H2O is not a linear molecule. It's a bent molecule. You won't know why until you take a higher level, but it's not a linear molecule. Okay, now I could draw this linear, but it's not how it acts. Okay, you'll learn that as you get to a higher level. Okay, it says the shape depends on the types of bonds and how many electrons aren't paired around the central atom. We'll talk about this as you guys get to a higher level. But remember when I showed this and I showed them kind of goofy like that? Do you guys remember me doing that? Do you remember why I did that? because those bonds are electrons, correct? And what do electrons do to other electrons?
Push.
They repel, right? So they're going to want to be as far away from each other as possible. But if I do this, do you see how there's a 90-degree angle between that and that?
Yeah.
And between this and this, it's 180 degrees?
Yeah.
That doesn't make sense, okay? And so we're getting into talking about what the shape would look like depending upon what's bonded on the central atom and how it's bonded. Okay? Now, I'm not going any deeper than that. Okay? Higher level, if you want. When you take chemistry, we'll go deeper into what is this shape. It's called a trigonal planar shape.
The more you know,
Alright, now this is very important. I can't tell you how important this is. It could be life or death.
Oh.
I doubt it.
You want to bet?
College or no college?
Alright, you want to bet?
Yeah.
How much?
1 penny.
How about your barbecue chip bag?
Alright.
What?
Sure.
Okay.
Do it.
No, you don't shake hands, you shake hands
You're not
first.
gonna like it.
It's not official to shake hands.
Okay, let me tell you something. You guys know what Tylenol is?
Yeah.
Okay, its scientific name is called acetaminophen.
Yeah.
Okay? Okay? Acetaminophen or Tylenol has a specific shape. If you take Tylenol and take its mirror image, exact same things bonded together, exact same types of bonds, you just flip its shape to the mirror image, it will kill you.
Oh,
I read that.
It will kill you.
that's
What do you mean
terrifying.
So like,
How fast?
this would be an example of a mirror image. Oops. That's not an example. So like, if I had a water molecule like this, its mirror image would be like, that's not good. Would be that. Now, for stuff like this, it doesn't make as much sense, but Tylenol is a huge molecule. It's a big molecule. Yes.
How fast would it kill you?
I don't know.
To Google.
So, being a pharmacist, you need to know your chemistry, don't you?
Y'all want Tylenol?
Okay, I'll take that bag of chips when you're done.
Only if I get
What if he takes them all and just goes to the
I mean, I don't know if you're a man of your word or not.
Just take a bag. Just
I don't know if he has integrity. We'll find out.
Whoa.
And this last slide.
There's one more.
Oh, I see the bottom.
That.
Just got on my hands. Nice.
We booked a shortened day tomorrow, right?
Yes.
Yeah.
Yeah,
Kinda.
it's 2 o'clock scheduled because of the
Water.
yeah.
I get a 0 day.
A 0 day?
We're flying to Colorado.
You think you're just so lucky?
Yeah.
He's gonna take the chip back with him.
Well, that depends on whether he has an ethical bone in his body or not.
I don't know.
He's gonna
Depends
give you the
on if he's a
Tylenol, man.
follower.
So watch out.
I don't know. I have to look back at my history book.
See the medicine. My dad always says, are you feeling sick? You want some acetaminophen? I'm like, what the heck is that?
Acetaminophen?
Acetaminophen. And he's just like,
Say that again.
Acetaminophen.
No, I was like, say
Say that 5 times fast.
Acetaminophen. Acetaminophen. Acetaminophen.
Okay, that wasn't that hard.
It's not at all.
Try saying the word toy and then boat probably.
Toy boat, toy boat, toy boat, toy boat.
Toe boy.
I got 3. That's my record.
Alright, here we go. Covalent bonds are weak. Okay? I'm telling you right now, covalent bonds are the weakest of all 3. Okay? Ionic bonds are much stronger. Metallic bonds are also stronger. It's very difficult to break an ionic bond by just heating it up. It's really easy to break a covalent bond by heating it up. Okay, because it's weaker. That's going to change a lot about what it acts like. You're going to find most, that's why you, oh shoot, Billy. That's why you see the guys that are non-metals over here, which we know those are the guys that are covalent in nature, correct?
Yeah.
Okay? They're in what form? Most of them. Gaseous form. But the guys that are metals tend to be solids at room temperature. And that has something to do with this. Let's see. This is the last one.
Oh.
Can we not do that?
Yeah, I want you to just put this in and then we can talk about it tomorrow. I know, I'm making you late for lunch.
I gotta microwave my chimichanga.
Don't do that to the dog.